Hello and welcome to lesson number 2 in Unit 6, Solving Problems with Quadratics in our grade 10 academic math class. So today we're going to jump into more specific styles of problem solving with quadratics. We're going to be looking at optimization problems, part 1. So there's going to be another lesson of this next. So when we use the word optimize, we're speaking specifically of an extreme value, either a highest or a lowest point. And this is a unique characteristic of parabolas, of quadratics in general, is that they have maximum and minimum values. They have a highest point and a lowest point. The shape, parabola, has only one unique point, meaning there's only one point that doesn't have sort of a partner across the axis of symmetry from it. That point is a vertex. When we're being asked to optimize something to find a maximum or a minimum value, what we're after is the vertex. So depending on the form of the quadratic, the form that gives us the vertex is vertex form. So the bulk of what we're going to be doing in the optimization problems is looking at questions where we're asked to find a maximum or a minimum value. We're going to either be given or create a quadratic in some form, and then we're going to convert it into vertex form by completing the square, usually. So, without further ado, let's jump in. This will be a bit of a longer lesson. I'm going to sort of take my time and go through every example. Most of the lessons in this unit will be like that. They'll be a little bit longer just because I want to make sure I'm going through every example that you see in the lesson thoroughly. So let's get at it. Example 1. The sum of two numbers is 16. Find the numbers if the sum of their squares is a minimum. So I'm a big fan of, once you read a question, try to find the clue that gives you an indication as to what you should be doing or finding or solving for. In this case, the clue is the word minimum. And I've already sort of got that done over here. When you see the word minimum, maximum, biggest, smallest, greatest, least, that's an indication that A, it's a quadratic equation, and B, that you are looking for the vertex. So in this question, the way it's been set up, we read the word minimum, we're like, okay, this is going to be a quadratic, and we are going to find the vertex. We are going to be generating two equations based on the information provided in the question itself. It says the sum of two numbers is 16. So for us, if we're going to translate that into sort of math, that's going to look like a first number, which we'll call A, second number, which we'll call B. The sum, when we add them together, is going to be 16. Actually, I guess I should have mentioned, I've also just sort of pre-written out the let statements here. It just takes a lot of time for me to write words, and it's not always worth it. So if you want to pause and write out the let statements, that's great. I've let A and B represent the two numbers that we're looking for, and I've let capital S represent the sum of their squares. So speaking of the sum of their squares, the second piece of information that we've been given is that the sum of their squares is a minimum. Now the minimum was a clue, but the sum of their squares is an equation that we can generate. So when we're talking about the sum of their squares, we're saying the sum of these two squares is going to be a minimum. So I have squared both A and B, and if I were to add them, create a sum, that's going to be our minimum value. So we've generated two equations here. One of them is linear. This is a linear equation that we've generated right here. In that the degree, the highest degree on any of our variables is 1. That's an a to the exponent 1, b to the exponent 1. That's going to be a linear equation. The second one is actually a quadratic equation because it is what we would call a degree 2 equation, in that the largest sort of exponent on any of our variables is 2. So we have a linear equation, we have a quadratic equation. We are going to, it's hard to solve a system like this where we have two sets of variables. So our goal here is to try to, as we did way back in Unit 1, we're going to be trying to eliminate one of our variables here. And the way we're going to do that is by substitution. So we are going to substitute number 1, which is our linear, into number 2, which is our quadratic. And I want to make a special note here because this is important. So we always substitute linear into quadratic. Always substitute linear into quadratic. Okay. So in this case, that means we're going to reorganize 1 to substitute it into 2. So we'll reorganize number 1. It's going to give us, and it doesn't really matter which variable we isolate here, but I will isolate A just because it's already kind of the first thing. So that will be A is equal to 16 minus B. So that's a reorganized number 1. Actually, I guess technically, why don't we make that a number 3? And then we'll substitute 3 into 2. Okay, so we're going to substitute reorganized 1, or 3, into 2. So the way we're going to do that is just write it out here. So we're going to write out S equals, now the A value is what we're substituting in, so in the space of A, we're going to be writing 16 minus B squared plus B squared. So just as a recap, again, when we're talking about substitution, we are replacing this A, which is right here, with something we know to be equivalent to A, 16 minus B. So we've substituted that in. So now we're going to expand out so that we have a quadratic equation that we can do something with. So in this case, I'm gonna run out of space, but I'm going to expand it out anyway. Now let's just recall that this is 16 minus B times 16 minus B plus B squared. And when we expand that out, we're going to expand this way, 16 times 16, 16 times negative B, etc. So I'm going to make the jump right now to my space saving section. Where should I go? We'll just go up over here. So we are going to have S is equal to, so 16 times 16 I think is 256. I'm just going to double check that. There we go, 256 minus 16B minus 16B plus B squared. So that's my expanded set of brackets, and there's my plus B squared. That was sort of the original piece that was there. And I'm going to gather together my like terms. So S equals, so we have 2B squareds hanging around. We have minus 32B hanging around, and we have plus 256 going on there. All right, so we have our quadratic in standard form. As I said, at the beginning, we saw the word minimum there, so we're looking for a vertex. So for us now, we're going to be completing the square. We do this, and fortunately enough, we practiced this in the pre-lesson to Unit 6. So we are going to common factor out the 2. We are left with B squared minus 16B plus 256. So now we have to determine what value it is that we will be both adding and subtracting. Minus 16B, so we're going to add something, subtract something, and there's our plus 256. So again, I'm not going to write this one out, but the way that we complete the square here is to take half of this B value, which is negative 8, and then we square it, which gives us 64. So we have plus 64 minus 64. As you remember, and I say this all the time, this completes our perfect square. This subtract 64 is there to balance our equation. Okay, so let's free that negative 64 from that bracket by multiplying it by 2. And let's see what the next line is going to look like for us. So we have S equal to 2b squared minus 16b plus 64. That's the part we're going to be factoring. And now we have 64 times 2. That's going to be rather negative 64 times 2. That'll be minus 128 plus 256. And now we factor and simplify. So here's our 2. Again, what's going to happen in our brackets? Well, it's going to start with a b. It's going to be a negative because we have a negative 16b value here, and that's going to be, as I said, 8. And we have minus 128 plus 256. That's going to give us plus 128. So there we go. We have here our vertex form version, which we arrived at from our standard form by completing the square. So what is my vertex going to be now? So vertex is going to be 8 and 128. Now let's just take a moment to unpack this, okay? So what we have here is a vertex, and the two variables that we've been using in our equation here are b and s. and those would correspond to x and y respectively. Let me just sort of jot that down. X as in an input and y as an output. So what we're saying here, our vertex is telling us that our b value, which is one of our two numbers, is going to be 8. And the y value, which is the 128, if we remember, we defined the capital S as the sum that is a minimum. So this is the smallest possible value that you can arrive at with a number 8, and we still have to figure out what A is, but it's telling us that 128 is that minimum or smallest value. So we need to do just one more thing here. We need to find A, because we've already found B. So find A. The way we find A is to substitute into A equals 16 minus B, which is going to be equal to 16 minus 8, which is going to be 8. So there we go. We have worked through this, and I'm just going to put a therefore statement on here. Therefore, the two numbers are 8 and 8. So there we go. Just to recap what we did here, we started off by reading the question and finding our clue word, and our clue word was the word minimum. It told us that A, this was a quadratic, and B, that we were going to be looking for its vertex. We defined our variables, A and B, as the two numbers we're trying to find. S as provided by the question, the sum of their squares. We created two equations, one that was linear and one that was quadratic based on their degree. We substituted, as we always will, the linear equation into the quadratic to try to eliminate one variable so that we can appropriately solve this, or in this case, I guess, complete the square. Once we substituted in, we expanded out and we simplified, which gave us 2b squared minus 32b plus 256. Then we completed the square. We found our vertex was going to be 8, 128, which corresponds to one of the numbers and the actual minimum value. We substituted our known value for b into the linear equation to solve for a, and then we wrote a therefore statement. So absolutely you should be looking at a question like this. This is a very common type of quadratic question that you would see when you're optimizing. The next two examples in the lesson are variations on it, but very similar. So we'll see you in part 2 of this lesson for a couple more examples.